Electromagnetic energy is the energy that's around us all the time. Some of it we're used to, so for example, light, but there's actually other kinds of light as well that we'll talk about in this area. And Isaac Newton discovered how light can be separated into different colors. He used a prism to separate white light from the sun into other colors, and that led into all kinds of interesting discoveries. And then later on, a guy named James Maxwell discovered that visible light is part of the electromagnetic spectrum. Electromagnetic spectrum is actually more than just visible light. It's actually infrared, which is used sometimes to heat food, ultraviolet, which gives me a sunburn when I'm out in the sun too long, but anyway, that's my problem. Anyway, it's also things like X-rays and gamma rays, as well as radio waves, lots of different kinds of things. And the interesting thing is that all of this led to the idea that light can be both like a particle sometimes and like a wave sometimes. It's a really fascinating thing. This is called the wave-particle duality. And if you look at me or I look at you, you look and I look hopefully like a particle, all right? We're made of mass and we have things that can be explained that way. But light sometimes will act like a particle, like you and me, and sometimes it'll act like a wave. And it's really a wild phenomenon. So all of these things we'll start looking forward to here in this chapter. It all comes down to really what exactly light is on the atomic level. So we'll look at that a little bit here too as we go through. This is an example of what Newton did way back a long time ago. And he took basically sunlight and he put it through a prism. And from the prism, you saw a whole bunch of different colors. And you might have seen this in your car, maybe if the sun comes through. You also see this in a rainbow, which is kind of cool. And the colors are all the different colors that we can see with our eyes. So red through purple, more or less. And they have different properties we'll talk about in this area. So normal light has all different colors inside it, the continuous spectrum. And we're going to talk about ways to then how we're just going to look at one particular kind of light, like maybe just red or green, but not purple and yellow, stuff like that.
Visible light is a form of electromagnetic radiation, which emanates from the source as waves. The waves are electric and magnetic fields oriented perpendicular to each other.
In physics, you'll talk more about what an electromagnetic wave is. But first of all, I just want to talk that all the things we're going to talk about are waves, all right? So they go up and down and up and down. Now, the electromagnetic waves have actually two waves associated with them. And you can see in that little picture there's like a red wave, which is up and down, if you will. And there's kind of like a gray wave, which is left and right, if you will. And one of the waves is the electric part, and one of the waves is the magnetic part, so that's where the electromagnetic wave comes from. We're not going to go into physics details as much as you would in a true physics class, but what's important for us is that the electromagnetic spectrum is a whole bunch of different types of different pieces around us. Now, visible light is definitely part of it, but also radio, microwave, infrared, ultraviolet, X-rays, gamma rays. It's pretty cool. And all of those have this kind of wave phenomena, all right? And we're going to talk about why visible light is different than, say, microwaves, and they're both different than X-rays, stuff like that. So what is a wave? Great question. A wave is just a movement that can transport energy. The matter usually remains where it is in place, but the wave will move and it can transport energy. And Maxwell there in the right-hand corner there was the one to talk about it. Now, in wave theory, there's a couple of important terms to talk about. One of them we'll talk about a lot is wavelength, and it gets the symbol there of lambda, which is kind of that upside down looking Y thing, I guess, for lack of a better phrase. Wavelength is actually nothing more than a distance. And we're going to see that that's a pretty important kind of thing when it comes to waves. Frequency, which gets the symbol nu. Now, nu looks like a little V. It's like an italicized V there, but really it's a Greek letter. It doesn't matter. You can write a V as far as I'm concerned. But anyway, frequency I like to think of as how many waves go by per unit time, like how many waves go by per second, all right? So if you have a high frequency, that means a lot of waves are going by per second. On the other hand, if you have a small frequency, then not many waves are going by per second. Node and Amplitude will be things we'll talk about briefly as well. Node is where there's no wave, and all waves go, if you can think about like up and down and up and down. And between the up and down parts, if you will, there's a node where there's no wave. And that's a really interesting part about wave theory. There's like nothing there for a little bit, then it goes back to the wave, etc., etc. Amplitude is not as important to us right now, but amplitude refers to how high up and down the wave goes, and that has some implications. We won't talk too much about it, but I just want you to be aware of what it is. All electromagnetic waves that we're going to talk about, visible, microwave, X-rays, etc., travel through a vacuum at the same speed, and that speed is really important. It's 2.998 times 10 to the 8th meters per second. This is the speed of light, and it's a number we're going to use all the way, not only this chapter, but all the way through Chem 223, and it's really important that you know/memorize it, and make sure that you always use this value for C. Don't use other variants like 3.0 times 10 to the 8th. We need the 4 sig fig value, so that'll be really important. So just keep that in the back of your mind as we go through this. This picture shows two different waves. The top one is a visible wave, and the bottom one is an ultraviolet wave. Now, if you look at it, they both have the up and down and up kind of phenomena, all right, going on. That's no problem. But there's a couple of interesting things we can glean from it. First of all, the wavelength is literally a distance, all right? So you can see there for the visible light, the distance is literally where the wave starts and stops. And it's literally a length. You can measure it like meters, centimeters, nanometers, stuff like that, all right? So the wavelength is literally the distance from where the wave starts and where it stops. Now in the ultraviolet, we have a wavelength too. Now you can see it starts where it starts going down and then ends where it goes up. That's fine, doesn't matter, it's a wave. Notice that the wavelength is smaller for ultraviolet than it is for visible, and we'll talk more about that later. Now, another thing that's really important for a wave is the frequency. And I told you earlier, it's kind of like the number of waves that go by per second. Well, let's pretend that the time here, t, and this is a time axis, the x-axis. We'll say that it's the same time. Say it's a second, whatever you want, okay? Anyway, in the visible light, you can see there's one full wave there, and then half of a wave right there. So the time it took to go from 0 to t was 1.5. So we would say that the frequency here is 1.5. They don't usually say waves like per second or waves per time. They'll just put per time. We'll talk about that later. Now on the ultraviolet though, notice here, if you start at 0, you've got one wave, you've got two waves, and three waves. So the frequency here is 3 waves per time, 3 waves per second, if you will. So for this problem, for these two types of EM radiation, we would say that visible light has a longer wavelength, a bigger distance from where it starts to stop than ultraviolet does. But we would say that ultraviolet has a higher frequency than the visible light, i.e. 3 waves go by per unit time instead of 1.5 waves per time. So you can see here that as wavelength goes up, the frequency goes down, and as the wavelength gets smaller, the frequency gets bigger. And we'll talk more about that here in a little bit. Now, I talked about nodes earlier. Node is like an area right there where there's literally no wave, all right? So there's lots of nodes on this piece right here. There's a node right there, there's a node right there, there's a node right there. Every time the wave goes through that 0 point, that's where you have a node. And nodes are going to be important to us here pretty soon. Now the amplitude we won't talk about too much, but the amplitude is literally just how big, if you will, it is from the baseline to the top of the wave. And there are some cool uses for that in science, but we won't talk about it quite as much, but I want you just to know what that term is. There's actually several kinds of waves. I think of waves a lot of times as at the ocean. So if you go to seaside or someplace like that, you watch the cool waves come in and out, and it's kind of mellow and stuff like that. Well, we're actually going to use what's called a standing wave. So imagine that you and I have a rope, and we're each holding on to the rope with one hand. and we start to shake the rope, all right? Well, the rope itself will go up and down like those people, like the person they're holding the rope will. So you can have waves and wavelengths and frequencies depending on how hard we would move the rope up and down. This is called a standing wave because the wave doesn't move. So at the ocean, you have moving waves, transverse waves, and that's a different kind of wave that has a lot of cool uses as well. But in what we're talking about, we're going to talk about standing waves. Now, what usually happens if you look at the animation on the right is at that midpoint, that's going to be the nucleus, and the waves will represent electrons and stuff like that running around it. So just realize that that node is going to be a place where the electrons are probably hanging out, and there can be different amounts of waves and frequencies, et cetera, going through. Frequency, as I said, gets the symbol nu. It looks like a V. That's fine. You can think of a frequency as waves per second or cycles per second, which is a more science name to use. And what a lot of times people use is they'll refer to the frequency in units of hertz. And a hertz or an Hz is like the number of waves per second. So a lot of times you'll see just per second or second minus one, something like that. Pretty wild. Waves also, though, have a wavelength, which gets the symbol lambda. And wavelengths are units of length. So they can be meters, nanometers, kilometers, millimeters, all kinds of different things like that. All radiation follows the speed of light, travels at the speed of light if you're in a vacuum. And what Maxwell and other people found is that the frequency times the wavelength equals the speed of light, c. So if the wavelength is in meters and the frequency is in 1 over seconds or hertz, then you can get units of meters per second. And that's where this all pops in. And so this is really important for electromagnetic radiation. It always follows the speed of light. So again, know the speed of light. This is also a way to see how, because the speed of light is a constant, if one of those goes up, frequency or wavelength goes up, the other one goes down. So big or long wavelengths would have smaller frequencies, and big frequencies, lots of waves going by per second, would have small wavelengths. So again, you've got to use 2.998 times 10 to the 8th meters per second. Don't use any other versions of it and stuff. 4 sig figs will get you through fine. So when it comes to visible light, all right, visible light have a whole bunch of these different electromagnetic radiation. But why is red different than green and green is different than purple? Well, in the right-hand side right there, that little video is showing, and it's showing how the wavelengths are getting longer. And as the wavelengths get longer, the frequency gets smaller. But look what happens to the color, all right? So the color is going there from kind of like an orange color, and it's going to go probably here a little bit now to like a red color. So what we find as scientists is that red wavelengths are pretty big for visible light. All right, so you can see in the left-hand side there, red is usually about 700 nanometers or so. And then blue and purple and indigo, those kind of things, have smaller wavelengths. They're more like 400 nanometers. And so it's a spectrum, all right? And that Roy G. Biv, maybe you've heard about that. That's a cool way that sometimes people know the different colors and how they go. So red is the longest wavelength, and violet is the smallest wavelength. Green is kind of in the middle. And as you change that wavelength and frequency, then you start changing the properties of it. This is what our eyes are used to, which is pretty cool. So it allows us to tell the longer wavelengths from the shorter wavelengths, stuff like that. Pretty awesome. Let's say that we have red light with a wavelength of 700 nanometers. Now note the dot right there. That means that that's a 3 sig fig number. Also notice that we're using nano, which is one of the metric prefixes. We can use this information to calculate the frequency of red light. But the first thing we've got to do is we've got to turn the nanometers into meters. Now, nano is 10 to the minus 9. So that means that a nanometer is 10 to the minus 9 meters. So you take your nanometers, multiply by 10 to the minus 9, and you should get 7.00 times 10 to the minus 7th meters. So we need to convert nanometers to meters, and visible light is almost always in nanometers, just FYI. But once you have it in meters, that's when we can use the speed of light. Because the speed of light equals the frequency times wavelength, we want the frequency. So frequency is going to be speed of light divided by the wavelength. So you can see there we've got 2.998 times 10 to the 8th meters per second. That's the speed of light. We divide it by the frequency in meters. So you can see the meters there cancel out. We're left with 4.28 times 10 to the 14th inverse seconds. That's what that thing means right there. Sometimes you see this as 1 over seconds like that, same thing. And what that again represents, you can think about that as the number of waves that go by per second. So there's 4.28 times 10 to the 14th waves going by per second when you have 700 nanometers of red light. Using second minus 1 or 1 over seconds is kind of weird. So a lot of times what people will do is they use hertz. And a hertz is literally an inverse second, 1 over second. So you'll more often see this listed as 4.28 times 10 to the 14th hertz. And there's a little joke, calculating frequency. It's so easy at hertz. Hertz was the person that they named it after, definitely. If you ever do a lot with radio, if you listen to radio, AM radio is usually in a kilohertz frequency, so those numbers times 10 to the third. On the other hand, FM radio is usually a megahertz, which would be 10 to the 6 hertz. So anyway, you'll start seeing things like this around you. So radio waves are also part of the electromagnetic spectrum, but they will have different frequencies than visible light. We don't see the radio waves, but we can see visible light. We can listen, though, for the frequencies, which is kind of cool. There's lots of different regions in the electromagnetic spectrum. They go all over the place. So visible light is right here in the middle, and it's a pretty small part, but that's what we use most of the time for light. On the other hand, if you get into smaller frequencies or bigger wavelengths, then you start to see infrared, or you don't see them, but you can detect them. I should point that out. Microwaves, which is what's used in our microwave ovens, if you have one. Radio waves are way down here. So those are all electromagnetic spectrum. They all have a wavelength and a frequency, all that kind of jazz. But you can tell on the top here that the wavelengths are getting bigger as you go right. So when you get to some radio waves, they can be up to 1 meter in length. While we saw earlier in that red light example, it's more like 10 to the minus 7th meters for red light. On the other hand, you can go to smaller wavelengths, higher frequencies. Those are the ultraviolet rays. If you get a sunburn, you know all about that, but there's a lot of cool uses for ultraviolet as well. X-rays, if you've been to the dentist, that's another version, higher energy. We'll talk about energy more in a little bit. And the smallest wavelength, largest frequency of all are gamma rays. These things are pretty powerful. We'll talk more about gamma rays later. But all of these have wavelengths. All of them have frequencies. They're all similar except in how big the wavelength is or how big the frequency is. And again, using the speed of light, you can turn the wavelength of one into the frequency and vice versa. No problem. There's an expression that's used to help know the different regions in the electromagnetic spectrum. It's a little weird, but rabbits mate in very unusual, expensive gardens. And so rabbits is radio and gardens is gamma. You get the idea. And so gardens here would have the highest frequency and rabbits would have the smallest frequency. Or in terms of wavelength, the biggest wavelength would be rabbits because they're inverse related to each other, and gamma rays would have the smallest wavelength. So here's a question you might think or talk about. It says, which of the following produces radiation having the highest frequency? All right. Highest frequency means largest frequency. So microwaves, radio, radar, and cosmic rays. So first of all, note that cosmic rays are not on this expression. Cosmic rays are a different phenomena that the sun creates when it sends particles out. It's not related to electromagnetic radiation. Radar is something you may not not know, but radar is actually a radio detection. It's radio detection and recognition. It's an acronym kind of thing. You can look it up. So radar is a type of radio. FM radio is a type of radio, obviously. But microwave is a little bit to the right of the radio things. So the highest frequency in this case then would be the microwave, all right? The microwave oven, which creates microwaves, has a little higher energy than normal radio waves or radar for that matter. And again, cosmic rays, not part of it.